Is it like on British YouTube?
British YouTube. the .uk one.
I don't think it's called that.
The secret word is cycloaddition. You will know what to do when you hear the secret word. Right? Okay, Friday's video didn't record, so at some point I'm going to come back in the room and scribble on the board a bit and yell at the camera, and we'll make that time up. Good, it's a lot more efficient when there are no other people in the room, so I could probably do that hour in 15 minutes. But we are here. This is a conjugated diene. It is 1,3-butadiene, and it undergoes electrophilic additions. It is non-threatening. We are not afraid of this molecule. Now some of us are afraid. What do you do with molecules that you're afraid of?
Change them.
You put your thumb over the threatening part. It's just a diene. We did dienes on Friday. We know exactly what they do. The fact that it's in a ring should not matter. You had bromine. And then there's CCl4 here, but that's just the solvent. Oh, I've got to give this thing a name. What's the name of my reactor?
Hexadiene.
1,3-cyclohexadiene. It's just a diene, it's a conjugated one. Write the product. We saw the mechanism. The mechanism was Friday. Mechanism is electrophilic addition of, we did HBr or HCl on Friday, but it's the same thing. You can add HCl to a double bond, then you can add Br2 to the double bond. But there was a twist, because this is a conjugated pi system. I have two products. Two products of electrophilic addition to a conjugated pi system, and they were called the 1,2 addition and the 1,4 addition. What's the name of my 1,2 addition product? Who's drawn it? One-two addition means that both of those bromines have added across the same double bond. Let's call this carbon number 1. That's 2, 3, and 4. I've got addition of bromine across that double bond. What's special about the addition of bromine across a double bond?
It's pure.
It's going to make the trans product. Its addition is anti, not syn. It makes the trans product technically the 3O product, not the cis, technically erythro product. How would I demonstrate that? There's a bromo, and there's a bromo. And what happens to this double bond?
Stays.
Yep. That's the product of my 1,2 addition. So its name would be
3,4 dibromo. Oops, yeah, trans.
trans 3,4 dibromo.
1 cyclo.
Cyclohexene. Do I need a 1 to tell me that the ene is at position number 1 in my cyclic molecule? No, I don't. In cyclohexene, the ene automatically is between carbon number 1 and carbon number 2. All right, that was the easy one. 1,4 addition. What's the name of my product? Sketch it. 1,4 addition. The incoming electrophile adds to this carbon, puts a carbocation here. Oh, that carbocation is 1 position away from a double bond. It's an allylic carbocation, which then rearranges to here to give me now, at this point, I have lost the thread of whether my bromos should be pointing up or pointing down, so I do not write any stereochemical notation for them. Because the carbocation has shifted, the atoms are not close to one another anymore. I've lost track of what I'm getting. There is, in computer nomenclature, a little wiggly line that says neither up, it's either up or down, I don't know, I don't care. When you're writing it out, just draw the line. All we're showing is regio, not stereo. Specificity. Name of this?
2,5 dibromo cyclohexene.
One of those double bond, one of those carbons on the double bond has to be carbon number 1. Has to be. So that's 1. This is 2, 3, 4, 5, 6. This is carbon number 1. 2, 3, 4, 5, 6. So this is 3, 6 dibromo cyclohexene. So we had 3 types of diene. What were they called? Isolated, where the double bonds are separated from each other by more than 1 sigma bond. Those pi bonds do not communicate. All right, that's interesting enough. Don't care. Cumulated, that's where both of the dienes touch the same carbon. That's too high in energy for us to consider them being products that we will deal with. We're not going to find a bottle in the stockroom of accumulated diene. It's not going to happen. And then conjugated, and conjugateds are the interesting ones because they do weird stuff. They do more than we were anticipating because there is a communication, there is resonance between these two, between those 2 pi bonds. All right, when we showed resonance of the carbocation, in the absence of the carbocation, I would move that pi bond here and then break that bond right there, and I would put a positive and a negative in this molecule. I will show you that later. Because it's not great. It's way, 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 way down on the list of the hierarchy of things that you can do. Okay. All right. conjugated dienes are areas of blank electron density, and therefore they're going to react with blank. What's the first missing word? If one of the reactants on your page has lots of electrons, it is electron rich. It's an area of high electron density. What is it going to react with? What's the second word?
Electric.
That's what we've seen. We've seen the double bond open up, reach out and grab hold of an H+, or in this case a Br2, and we all at this point should be familiar enough that you can induce a dipole, push the electrons to the back of that molecule, make the back of the molecule be a little bit negative, and the frontier of that molecule be a little bit positive. Okay? That's your electrophile. And dienes should be reacting with molecules that do not have lots of electrons. So what I'm about to write on the board makes no sense at all. Here's a conjugated diene. It's butadiene. We're going to keep them all nice and simple. If they're symmetrical, then life is easy. If they're asymmetric, then stuff gets kind of difficult. All right, area, high electron density. This is a diene. What's the last thing in the world that it's going to want to react with? Another area of high electron density. So if I were to bring in an alkene, there would be no way that those two molecules should interact with each other. And yet, when I heat them up, they do. Butadiene and ethene don't do this reaction particularly well, but it's the nice stripped down version of what's going on here. Make cyclohexene. And that makes no sense at all. Two guys. Diels and Alder recognized that a conjugated pi system will interact with another pi system in a reaction that closes the gap between those two chains in a cycloaddition. I said the magic word. I said the secret word.
Oh shoot. Dang it.
This is a cycloaddition. And that needs to be explained. And we're going to explain it this way, that I have a diene, and now my alkene is a special type of molecule in this reaction, which gets to be called a dienophile. And this reaction on the surface kind of looks complicated, but oh boy is it simple, because it always makes this template. Whatever it is that I put here, and I'm going to throw all sorts of variations at you, it always makes this. So you're going to get your reactants to come together to make a cyclohexyl ring with the points up and the double bond on the left. Okay? It's always going to be templated to that shape. Okay. In reality, yes, we can make that reaction work, but we need something else. We need an R group here. And that R group needs to withdraw electrons. So in reality, the dienophile needs an electron withdrawing group as a substituent. All right, I got to figure out what an electron withdrawing group might look like. Don't scare them away. We have two types of substituent. Those that push electrons into our reaction, and those that pull electrons out. What I need is the second here, and you can always recognize an electron withdrawing group by the atom that is directly attached to the dienophile, which is now my alkene. The atom that is directly attached to the dienophile is also multiply bonded to an electronegative atom. All right, let's pause for a second and think what that means and how to recognize it. The dienophile is my alkene. The blue group right here is my substituent. It needs to be an electron withdrawing group, which means that the atom that is attached to the alkene is also multiply bonded to an electronegative atom. All right, periodic table. What's our most electronegative atom? Fluorine. How many bonds can fluorine make? One. Can anything therefore ever be multiply bonded to a fluorine? No. Fluorine can only make one bond at a time. Therefore, fluorine, chlorine, bromine, iodine, not part of this conversation. I need to be multiply bonded to an electronegative atom. Identify for me an electronegative atom that can accept a multiple bond. Oxygen. Oxygen is in group 6. Always makes 2 bonds. Could be a double bond. Or a nitrogen. Nitrogen makes 3 bonds. So you could make a triple bond to a nitrogen. So we're going to see stuff like that. That gives me groups. So here's my diene. Now there's my dienophile. And then here's my electron withdrawing group. The atom, in this case a carbon, that is directly attached to it is doubly bonded to an electronegative atom. That's an aldehyde. Or a ketone. Or a carboxylic acid. Or an ester. All of those are electron withdrawing groups. They are aldehydes, ketones, carboxylic acids, esters. All in the carbonyl family. These ones are in the carboxyl end of that family, and these are in the carbonyl end of that same family. I could, still with a carbon, make a triple bond to a nitrogen. Oh, what's that called? That's a cyanide. We call them cyanides when they're inorganic, and we call them nitriles when they're organic. So I've got aldehyde, ketone, carboxylic acid, ester, nitrile. A couple of other things could be there. Think of another group that has an atom that is then multiply bonded to another atom, and that atom has to be electronegative. Now an amine, that's an amine. There's no multiple bond here. So, nope. But I could start with a nitrogen. Here's a nitrogen. There's my dienophile right here. What could I attach to this nitrogen that would be a multiple bond to an electronegative atom? Knowing that nitrogen has to make 3 bonds.
Oxygen.
That's a nitro group. You can't do the nitro without a separation of charge. There has to be a positive on the nitrogen and a negative on one of those oxygens, and those oxygens take it in turns, holding on to the negative by resonance. Resonance says move the negative in the direction of the double bond, and so you zigzag. Oh, the negative's now here and the pi bond is there. And that negative moves up and down. You could also something like that, which is a sulfonic acid. These ones with the carbons are the ones that we're going to see the most of. Those are the ones we're going to see later under another scenario, not so much in the Diels-Alder. all of the stereochemistry in a Diels-Alder is retained, it's conserved. So if I have something special going on in this fragment, I keep it when it reacts with that one. And the same here. So let's do a few examples and see that that is the case. All right. If I take my diene and I react it with this nitrile, dinitrile now, here's the reaction. The double bond from here reaches out and grabs hold of one of those carbons. So the reaction starts from a bond and goes to an atom. That carbon already has 4 bonds. We haven't written one of them in because it's to a hydrogen, and we've left that off. But it has 4 bonds. So it's going to have to let go of one. It's going to let go of the weakest bond that it's holding. What is the weakest bond that it's holding? The pi bond is the weakest bond that it's holding. And the electrons in that pi bond move over here. Well, that carbon already has 4 bonds. Double bond to a carbon and then 2 bonds to hydrogens that we can't see because we've left them off. It's already got 4 bonds. Trying to make a new bond to it, it's going to let go of its weakest bond. What's its weakest bond? The pi bond. And the pi bond shuffles down to here. You always make the same templates. I have 2 new bonds. The bonds are right here where the orange arrows went. I've made new bonds, right here. Those are new. Now, how would you describe the relationship between these 2 nitriles in the dienophile? What's their relationship?
Cis.
They are cis, and if they are cis in the reactants, then they get to be cis in the product. If my dienophile was trans, I would like to see, when you repeat this back to me, that it's clear that the arrow starts at the middle of a bond and dead ends on an atom. There used to be somebody with whom I worked that would draw their reactions like this. But no, there's nothing here. Where's that arrow going? That doesn't make any sense. Show me where the arrow starts and where the arrow finishes. It starts as pi electrons and it finishes as sigma electrons. Same template. every single time. You make the double bond, you make the cyclohexene with the double bond vertical and to the left. Now, because the dienophile was trans, you get this. Here I have my double bonds are now internal, but they're internal the same way. This is the EE, or the trans. I like these orange markers. All right, the relationship across the double bonds in the diene is that both of those double bonds are trans. They could both be cis, they could both be ZZ, or they could both be E, be the EE isomer. But as long as they are the same, then those substituents end up also being the same. If one is the E and one is the Z, template. And now one is up and one is down. They were different in the reactant. They're going to be different in the product. Okay. Let's make things a tiny bit more interesting. There's my diene. Here's my dienophile. At this end, I'm going to add a carboxylic acid. At that end, I'm going to add a carboxylic acid. And instead of being a double bond for my dienophile now is a triple bond. Reaction some heat. See what you get. The mechanism is the same. Now we tend to write this out as if it's a cascade of electrons, but it's not. It's much more complicated than that. Those arrows all move at the same time. That is a concerted reaction, and it's what we're going to call a 4 plus 2 cycloaddition. That is not 4 carbons and 2 carbons. It's not a 4 carbon fragment and a 2 carbon fragment. It is 4 pi electrons and 2 pi electrons. And this reaction works when the alignment is correct, that this is a molecular orbital. And when the lobes on this molecular orbital line up with the correct symmetry of the lobes on that molecular orbital, then the reaction progresses. So it's a lot more finessed than we give it credit for right here. All right. Well, I've never seen this before. I don't know what's going to happen, but I do know that every single Diels-Alder cycloaddition makes the same template. So I have to get some credit for that. I've written out what the backbone of my molecule, my product molecule looks like. Now all I have to do is figure out where the other stuff goes. And there's nothing on this 4 carbon fragment, but there is stuff right here. What's missing? I started with the triple. I've only used one of the pi bonds. The other pi bond is still there. When I start with the double bond, I use the pi electrons and I leave the sigma electrons behind. If I started with the sigma and 2 pi's, use one set of the pi's, leave 1 sigma and 1 pi behind. So I've still got a double bond right here. If you keep these reactions symmetrical, they will reward you with one product. If you make them be asymmetric, oh, you're asking for trouble. Asymmetric reactions have more than one product. All I'm going to do is tell you that this is possible. I'm not going to go into the details. Usually, I haven't checked that our textbook has this, but I think it does. We talk about these cycloadditions early on, whatever chapter we're in now, 10 or something, 11, something like that. And then they come back and they do them again under the general umbrella of what they call pericyclic reactions, which will be in like chapter 27, because there's a lot to see here. And they can't possibly cram it all in to this chapter without completely bogging down what it is that your arc of education is supposed to do. You're supposed to be able to recognize a handful of reactions and use them. So it does get kind of more complicated. So if I have an asymmetric diene and an asymmetric dienophile, to make some of this and some of that. And it depends. This reaction is not what it seems on the surface. It is much more complicated. Or, another way of looking at it, once you learn how to read molecular orbitals, it's actually much more simple. And it depends. Does this pull electrons? Does it pull them hard enough? Does this push electrons or pull electrons? And does it do it hard enough? Because I've got frontier molecular orbitals right here that might be in the shape of a P, and they have to overlap right here. And if you make those balloons big because you're pushing electrons into them, or you make them small because you're pulling electrons out, then the fragments either fit this way, or they decide to flip around and fit the underside. Again, that's a topic for much, much later. Asymmetric ones are a problem, as are these. If your reactants are already part of a cycle, you're going to get something you weren't expecting. Here's butadiene. Here's a dienophile. Okay. So far, I'm not threatened by this. Okay, we've seen this. I have a symmetrical diene. I have a symmetrical dienophile. They do the concerted 4+2 cycloaddition. It makes me one product. I have opted, because this is cis, both groups are on the same face of my product molecule. I've decided to write them pointing up. What if this were a question on the test and the answer key said that they were pointing up, but you had written that they were both pointing down? Who's correct?
Both sides.
Everybody's correct. Because if they're both pointing down, but this molecule is symmetrical, then that is the same as this. It's the same thing. It's got a plane of symmetry that runs right through the middle. Right? The new bonds are here and here. All right, we're all good with this. What if, instead of being butadiene, it was cyclopentadiene? What if? Now, I have an additional atom that sits here that I have to describe somehow. Does my black pentagon fragment of my reactant, the orange bonds are the new bonds that I've made. It is still there. The question is, this carbon right here, that carbon right there, has a bond, a bond, a bond, and a hydrogen. That's a tetrahedron. Which means something is pointing away from me, two of them are in the plane of the paper, and something is pointing out towards me. If these are both pointing out towards me, are those ketone groups still pointing away? I don't know. So by definition, we write, this is a bridge, we write the bridges pointing out towards us. There are two products here. There are two isomers. There is the isomer where this part of the molecule is pointing towards you, and that molecule is, and that part is pointing away. And then there is this one where this is pointing towards you, and that is also pointing towards you. So this is called the endo isomer, and this is called the exo isomer. And on Wednesday, we'll bring the plastic models and we'll make these shapes because they are significantly different from each other in terms of shape. And then we'll determine which one gets made. Because one of them gets made when it's hot, and one of them gets made when it's cold.